Hello, calculus. We're going to do one more problem on finding the volume using the washer method. I would say if you felt really good about the notes from last time and you did all the homework and you have no questions, you don't necessarily need to watch this. However, it's probably going to be a good little refresher and can't hurt. So we'll get right to it. It says determine the volume of the solid obtained by rotating the region bounded by the following two curves, y equals x squared minus 2x and y equals x, about the line y equals 4. So of course, the best way to start is going to be to sketch this out. So I'm going to start with an x and a y axis. Oh, that was terrible. Whatever. 1, 2, 3, 4, 5, 6. We'll say 1, 2, 3, 4, 5, 6. And I'm going to start with the line because that's easiest. The line y equals x, we know has a y-intercept of 0 and a slope of 1, so it's going to be something like that. Let's see if I can draw it. Okay, that was not terrible. Wasn't perfect, but hopefully you'll forgive me. All right, again, that's the line y equals x. So I'm going to add in arrows and write that here, y equals x. Okay, and then I have the curve y equals x squared minus 2x, which I'm going to start actually by factoring quick. So x times the quantity x minus 2, because that helps me see my y-intercepts really quickly. Excuse me, my x-intercepts really quickly. I have 0, 0, and 2, 0. And then I know that this parabola is opening up, so I can be pretty confident that it's going to look something like that. Again, y equals x squared minus 2x. Now, I didn't do these perfectly to scale, but one thing that we do want to notice is where they are intersecting. So this point and this point, because here is the region I am interested in rotating. And if I want to find those 2 points of intersection, well, I know this one, 0, 0. Easy. But what about, there we go, that looks nicer. What about that point? How will I find that point? You can kind of see it on my graph. It's not perfect, but because I didn't scale this perfectly, we could also do solve for that point by setting them equal to each other. X squared minus 2x is equal to x. I'm going to move that over. X squared minus 3x is equal to 0. Factor. X times the quantity x minus 3 is equal to 0, and this gives us our 2 points. This is our origin, where they intersect here, and this, x equals 3, is the point 3, 3. How do I know it's 3, 3? Well, I know it's on the line y equals x, so it's pretty quick. I could also plug in 3. 3 squared is 9 minus 2 times 3, which is 6. 9 minus 6 is 3. All right, so I've got a lot of good things here. I'm going to pause and just kind of make this a little nicer. All right, here's the tricky part about this problem. We are rotating this about the line y equals 4. So 1, 2, 3, 4. Was that 4? 1, 2, 3, 4. Okay, here's our line y equals 4. Let's see if I can make a straight line. Well, not terrible. Again, forgive me. Okay, this is the line y equals 4. And we are rotating around that line, y equals 4, meaning I'm taking this and going around this way. Okay, this is a little different than all the problems we've seen so far because, again, we're not rotating around the x-axis or the y-axis, we're rotating about a different line. So let's consider how we're going to do this. If we are rotating it around this line y equals 4, imagine going around in circles from left to right, right? We're going around this way from left to right, which means we're doing it with respect to x. I'm moving from left to right, which is the x-axis. Okay, so that helps a lot. That means I'm going to take the antiderivative from this x of 0 to this x of 3. So from 0 to 3. And it helps because I'm going to do this, again, with respect to x, so I know it needs to be in terms of x, dx, from left to right. Now, I need to find two things. I need to find the big radius, which technically in this case is going to be, I'm going to make that capital R, from this line to the parabola, and I need to find my little radius. So it's going to be from that y equals 4 to the line y equals x. That's going to be my lowercase r. Maybe you can already see what capital R and lowercase r are going to be, but I'm going to talk you through it anyway. Imagine this point right here. Let's say this is the point 1. If I plug in 1, what am I going to get? I'm going to probably get -1. 1 squared is 1, minus 2 is -1. Okay, so I'm talking about this point on the parabola. The y value is what we're focusing on here because I need to figure out this total y distance. If I am at -1 here, how far is it? I'm talking distance to the line y equals 4. So it's a total distance of 4 plus 1, right? The total distance is 5. Okay, how could I get this anytime? Well, if I take my 4 and I subtract from it the -1, I would technically get 5, which again is what I want for that distance. So can we generalize this for our big radius to be 4 minus whatever the y value is in this case, which we know based on our curve is x squared minus 2x. That's going to be our big radius. Our little radius, I think, is probably a little easier to tell or to see. Again, we're looking for this distance here, so it's going to be whatever this line is, in this case 4, minus whatever our line is at. So, okay, again, if I pick this point right here, 1, 1, I'm not looking at the y value of 1, I'm looking at what's left over, the space in between. So the whole thing is 4, I want this distance, which would be 3, or 4 minus x in this case, because we're looking at the line y equals x. I have my big radius, I have my little radius, I can now plug things in. So I have pi, right? We always have pi, and then I have my big radius squared. So I'm going to write that as 4 minus x squared plus 2x, that whole thing squared. Notice I distributed the negative, and then I have, put big brackets, minus my little radius squared, 4 minus x squared, and end bracket, and then I'm going to pull this dx over a little. Here is my integral. To be honest, from this point, if you want, you could use your graphing calculator and plug that all in. You'd have to make sure you put correct parentheses. If you want, you could also FOIL this all out and simplify. I'm not going to do the work for that because, let's be honest, you guys don't want it and you don't really need it. So I'm just going to write down the answer. If you want a worked out solution, I am so happy to give it to you, but you probably have been using your graphing calculators all this time anyway to solve these, so keep doing that. If you're not, just a reminder, if you click the math button, math, and then you scroll either down to 9 or up to 9, it's function integral. So fn int, and this will give you something. It kind of looks like this. It's got a box, there's a box, and a box, and then D box. So you're going to type in all the pieces in these spots, and then you solve. And if you do this, hopefully you get about, we'll go 96.13 units cubed. Remember cubed because we are finding volume. Again, you totally can do this all by hand. In fact, you are all smart enough to, but right now we can use our calculators, so why not? If you have other questions, please let me know. And I miss you, and I guess I won't talk to you again, but I probably will, so we're not even gonna say goodbye. Okay, bye.